Hello everyone, welcome to my virtual presentation on virtual, augmented, and mixed reality tools in soundscape evaluation and design. My name is Ban. I'm a research fellow in the School of Electrical and Electronic Engineering in Nanyang Technological University in Singapore. I will be showcasing two immersive display applications, one based on a virtual reality head-mounted display and another based on a mixed reality head-mounted display. Before going into the details, I will first give some background behind what motivated us to build these applications. This begins with the auditory sensation in soundscape and how it is influenced by visual inputs, giving rise to a multi-sensory audiovisual perception. This is followed by a summary of some of the immersive display technologies that can be used to investigate these audiovisual interactions, in particular, virtual, augmented, and mixed reality displays. Finally, I will give an overview on some of the experimental methods used in the subjective evaluation of sound. After the background, I will explain the current state of audiovisual stimuli evaluation in VR, then jump right into the details of our VR application, before coming back again to describe the motivation behind our mixed reality application, followed by its details. There will be a demonstration of the functionalities of both applications. For the benefit of anyone who is not familiar with the notion of soundscapes, it is defined in ISO 12913 Part 1 as the acoustic environment as perceived or experienced and/or understood by a person or people in context. This process is described in Figure 1. It is interesting to note that there could be a number of factors that can influence the interpretation of the auditory sensation, such as attitude-related factors like experience and expectations, and other sensory factors like visual impression and smells. It is perhaps well known by now that vision can greatly influence the interpretation of sounds and vice versa. One of the best known audiovisual illusion is the McGurk effect. The image shows a man repeating two different syllables, far with an F on the left and bar with a B on the right. If a sound clip with the man sounding bar with a B is paired with the image of him pronouncing far with an F, it will seem like far was heard. This illusion works even if you know about it. You can check it out in YouTube by searching for the McGurk effect. This illusion demonstrates the multisensory integration of audition and vision into a new and unified audiovisual perception. Processing of both senses are not independent of each other. Unsurprisingly, a recent review of audiovisual interaction studies in soundscape and urban noise has reflected an increasing number of studies considering audiovisual effects in the perception of the acoustic environment. The increasing availability of virtual reality technology also resulted in a shift towards mostly VR-based evaluation methods since 2017, as reported by Li and Lau in their 2019 paper. There has been some confusion as to what is called virtual, augmented, and mixed reality technologies. To avoid ambiguities, we have adopted the recent standard set by the Consumer Technology Association. Therefore, virtual reality is defined as a fully immersive user environment that affects or alters sensory inputs. Most VR content is now consumed on head-mounted displays, or HMDs, as shown here. Modern VR HMDs usually offer 6 degrees of freedom tracking and can be either a fully wireless standalone device or tethered to a PC or laptop. Augmented reality is described as technology that overlays digitally created content into the user's real-world environment. This is exemplified in the recent release of Google Maps AR, where the wayfinding instructions are overlaid onto the environment through the camera on a mobile phone. It is important to note that visual objects are overlaid onto the screen but do not interact with the environment. This brings us to mixed reality, which is often used interchangeably with augmented reality. Mixed reality is defined as a technology that blends a user's real-world environment with digitally created content. where both environments coexist to create a hybrid experience. This includes occlusions and shadowing, as shown by the demo on the left. You can see that the car gets occluded as it travels under the table and you can climb up the sofa. So it interacts with real objects in real time. At the moment, there are perhaps only two well-known mixed reality head-mounted displays, the Magic Leap 1 and Microsoft's HoloLens and HoloLens 2. As introduced earlier, sound is subjective in nature, and there has been a large number of subjective evaluation methods developed across many subfields of acoustics. For instance, audio quality evaluation, psychoacoustics, and soundscape evaluation, just to name a few. These methods can be represented in five main groups, namely discrimination, integrative, descriptive, temporal, and performance methods. Some well-known discriminative methods include ABX and PET comparison, and integrative methods include affective quality like hedonic scaling and audio quality methods like the ITU MUSHRA test, both of which are implemented in our VR application. To conduct an audiovisual subjective evaluation in VR is no easy feat. To integrate an interface into the VR environment, it requires some knowledge of computer coding. There is also usually a lack of compatibility with existing workflows in digital audio workstations. Currently, VR-based audiovisual evaluation studies usually involve eliciting a verbal response from the participant or post-evaluation of the stimuli based on memory, just to name two of them. These methods are not only time-consuming but could bias the results and introduce unnecessary fatigue. Hence, there appears to be a lack of accessible tools to conduct audiovisual evaluations in the VR environment. Therefore, we have decided to build a VR application framework for the subjective evaluation of audiovisual stimuli that is intuitive, such that both the participants and investigators require minimal training. It is also modular, in which questionnaires can be easily modified without diving into the source code, and future methods can be added onto the platform easily. Lastly, it should be compatible with modern VR HMDs and can be integrated with popular digital audio workstations. The conceptual framework is summarized in this diagram, whereby the VR application, highlighted in yellow, handles all the synchronization between the individual modules and sends the video stream to the VR head-mounted device. The audio stream is handled by the digital audio workstation, and it's synchronized via the Open Sound Control protocol. The Open Sound Control also sends your pitch and roll information so that the sound field can be rotated accordingly. The participants will interact with the questionnaire shown on the screen using a handheld controller. This questionnaire and subjective test interface is loaded from a separate database. At the end of the subjective test, the survey response is stored as a text file. The application is built with Unity, the most widely adopted platform for VR applications. The technical details are provided in the conference paper, and we have uploaded the source code to GitHub, along with some instructions for anyone who wants to test out our application on their own. The link to the GitHub repository will be shown at the end of this presentation. We tested the application in the HTC Vive Pro platform and using the Reaper digital audio workstation. We have implemented a hedonic scaling example into the VR environment as shown in the snapshot here. Participants will select the corresponding answers using the handheld controller guided by a laser pointer in the VR environment. The questionnaire shown in the previous slide was loaded from a text file as shown here. This is a regular text file that can be edited using Notepad on Windows or TextEdit on the Mac. An animated example is shown together with the digital audio workstation interface on the left, which is in sync with the video. Subsequent questions are automatically loaded after the participants select their answers. You can see the laser pointer in action here. A slider-based rating scale similar to the ITU MUSHRA test is shown here. The sliders can be controlled via the handheld controllers. The playback of the audio stimuli is controlled via the small media button next to the slider. which selects the respective track in the digital audio workstation through open sound control communication. Moving on to the next potential gap. Outdoor soundscape design or renovation has yet to be commonplace. This could be partly attributed to the high cost of design iterations, especially with physical structures like barriers or water features. One way to experience the design changes without building the structures is through simulations with virtual objects in virtual reality. However, traditional simulation software in virtual reality is usually quite restrictive and do not allow you to manipulate virtual objects in real time. There is also a lack of real-time feedback in terms of objective measures like sound pressure level. Hence, we believe that a mixed reality-based platform could be useful not only for the design of soundscape, but also its evaluation, especially for renovation of existing spaces. This will allow for real-time interaction and manipulation of virtual audiovisual objects such as water features or speaker installations. Display of real-time objective measures such as sound pressure level could be useful for designers to decide on and evaluate the sound levels of their intervention in situ. We built an MR application for the first generation Microsoft HoloLens, which is also developed in Unity. Functionalities such as gesture inputs, spatial audio, and 3D environment sensing are called from the Mixed Reality Toolkit SDK provided by Microsoft. Supplementary scripts were written to provide additional functionality not available in the SDK, such as sound pressure level display. The application was then deployed onto the HoloLens through Visual Studio. There are two main functionalities: manipulation of the audiovisual objects and real-time sound level information. The audiovisual objects, like the fountain shown over here, can be virtually inserted into the real-world environment and manipulated with hand gestures to rotate, resize, or translate. The sound emitting from the object is spatialized such that it sounds like it is originating from its position in space. The instantaneous SPL information and a 1-minute equivalent average is computed from the onboard microphones and displayed on the screen as shown in a snapshot here. The overall interface with two audiovisual objects inserted looks something like what you see on the screen here. Useful information like the SPL is augmented onto the field of view, whereas audiovisual objects are anchored to real-world positions. The volume levels of individual objects can be adjusted via the volume bar as shown, or by tapping on the increment or decrement buttons. The objects can also be manipulated with hand gestures such as translation, as shown here. The application of VR and MR is not limited to what we have shown here. There is also more to be done to improve our current setup and to test them with real users. Therefore, we welcome any suggestions or feedback which you think you would like to see as a potential user. We would like to acknowledge the support of our funding agency, the National Research Foundation Singapore, and the Singapore Ministry of National Development. Thank you for listening. You can see some of my other works on ResearchGate, and the link to our GitHub repository for the VR app is shown here as well. The AR application is currently being refined, and we will release it when it is ready. Thank you.